So welcome everyone. This is going to be the fourth episode of our research talk series on robotic AI in medicine. We're very pleased today to welcome Dr. Long Bai, who's an algorithm expert and senior research scientist at Alibaba DAMO Academy. His work focuses on generative AI for robot-assisted endoscopic surgery, particularly the use of generative and vision language models to enhance perception, reasoning, and decision support in endoscopic robotics. So Dr. Bai is going to discuss today how these models are reshaping intelligent endoscopic systems and enabling new forms of surgical assistance. So with that, I'll hand it over to Dr. Bai to begin the talk.
Thank you for the introduction, and also thank you for inviting me here to give the talk. And I would say that actually my research topic is very similar with the previous presenter, I think Yuming, and I and her her research and I is both mostly with the perception part of the surgical robots, but not the true actuation of the robotics. But in my talk here, in the end of my work, I will also share some of our words in the vision language action to see that whether how currently in the the big flow of the embodied AI, how we change from the perception tasks into these actuation tasks. So today my topic is intelligent perception and interaction for clinical AI collaborative robotic surgery. Okay, so the era of AI and robotic surgery has been discussed lonely by a lot of works, and we can see here in surgical procedures we have a variety of surgical procedures here, and all of these they may based on minimal invasive surgery. And in these kind of surgeries, if we have a robotic assisted it can be much more better surgical outcomes and also less harms to the patients. And also in the right part, we can see that currently we have so many surgical understanding tasks. And in the before ChatGPT come out, that in the I would say like in before the trend of foundation models, that every single surgical thing understanding task that we need to develop a single model to uh, to understand every different thing like the action recognition, the instrument segmentation, every task we need a single model for it. But now that we can use a large vision language model to understand all of these tasks and gives the AI gives the AI brain a very clear understanding to perform the following perception tasks to help the surgeons and also helps automate the surgical robot progress. And also in the Okay, let's go. Just move on. This is a short brief of today's talk. I'll talk about mostly in the four parts of my works, in the different procedures of the surgery. So in the first part, that when we have a lot of surgical images, and how we may have different kind of image corruptions, like the low light or the smoke or overexposed. So the first part I do is to do the restoration of endoscopic image restoration to make it to restore the image better and make it more clear for the surgeons to use it. And in the second part, so we do the interactive multimodal assistant. And for this part, we mostly use vision language models to make the model better understand the 2D images of the surgeons. And also makes the model to understand better, and it can also give feedback to the surgeons, and we can give better understanding in the 2D part to give the like understanding of that, and I will make it in detail later. And the third part is in vivo 3D perception, and we all know that in vivo tasks and in the anatomical structure is very complicated, and if we can have the 3D perception of that, and we can know the depths in vivo, so we can give a better warning and understanding of the dynamic environments, and then give a better perception understanding of that. And in the last part is for word simulation and actuation, and here we do the vision language action and also video generation, and we want to formulate our word model to formulate the whole procedure of the surgeries. Sorry. So let's go into the first part. The first part is in endoscopic image restoration, and we all know that maybe not everybody know that the endoscopic images we may have different kind of image corruptions like the low light and overexposed or smoke or bleeding, and all of these will hinder like important anatomical structure or the important action of the instruments. So maybe we cannot see very clear that what is the what is the target I need to work on, or what is the target, or what is the instrument is working on right now. So we cannot make it very clear. So currently, we need a restoration method to restore all of these images into the normal things, and then we can see better. So the restoration methods must be very precise and must be lightweight and real time, so it can be deployed in the very a very critical procedures with this lightweight and real time, and then it can give a better deployment performance. So my work first start with diffusion models. So we know diffusion models it has some advantages, like it has high precision and it also have better perceptual performance. But the real time and the lightweight performance problem is always a problem that we cannot make the diffusion very lightweight and make it real time to catch up with theoretical procedures. So my first work is on the MICCAI 2023. It means area caps, and this work is actually very simple. That, of course, at that time diffusion models just come out, and then we use a normal CNN branch with reverse diffusion, and we just concat them together to make the actually makes a network more deeper to give it better optimizing performance, to give better performance. So actually, in this work, we have very high PSN and SSN and all these kind of metrics, but actually the inference speed will be very slow. So there's a problem that we want to solve. So in the next work, we just in MICCAI 20, sorry, it's actually MICCAI 2024, and the best paper of MICCAI 24. It's we named this paper Light T-diff. It's lightweight diffusion models with T structure, and the idea of this best paper is actually very simple. So here in the normal diffusion procedures, we need to add noise in the add noise, and then remove noise, and just like this, we need to do all of these procedures step by step. But if we think that in the first steps, we can use the normal resolution here. In the first some steps, we can use a normal resolution, but in the middle steps, we don't need the normal resolution. We just cut the resolution into the 1/4 of the previous resolution, and then it will heavily couch the computational consumption here, but we can still achieve similar performance, even better performance through this way. So and this we can see the final performance and the parameters and also the FPS that through a very simple and straightforward way that we can get better performance and FPS in this task. And in the follow-up work, and we are also thinking another scenario that previously we focus on low light image enhancement because this is a very the data of this task is easy to access. But when we think that we have different kind of image corruptions, that we may have overexposed, underexposed, and we have the blood, smoke, and the low lights, a different kind of image corruptions, and maybe we should have one model to solve all of these programs together. Or if we have a model for deblooding, we have a model for desmoking, we have a model for like image illumination restoration. It's a very complicated system, and we cannot like we get each task and we use one single model. So this is not reasonable and not doable in real setups. So here we develop another system that we think we should like this. We should use one model to do the all-in-one image restoration to restore these images by a single task. So here, we also set up our procedure like we have different kind of inputs of different corruptions, but we should belong to a self-supervised prompt conditions. We should not have like the prior prompts into the model. So it's like cheating. So we want the model to learn the prompt conditions by itself. And however, we also want to collect such a prompt dictionary here to make it to do the task adaptive routing. So when we can learn the prompt by itself, like we just input a model, input an image. Sorry, I just input an image, and then the model can learn that it is image with smoke. So it can collect this information in its prompt dictionary. So it can do the task adaptive routing. So it should do the desmoking. So the smoke is a specific kind of corruption, and how to solve this kind of corruption is another routing way we can follow this routing to solve this problem. So here that we like actually the idea is also straightforward, that we just extract the extract the prompt information from the raw images from the FFT, and also a simple convolution layer here to collect this information and then store it into the prompt dictionary, and then we do the average pooling to put it into the main stream to do the final routing in the system. And we can see here we visualize the TSNE, and we can see previously that all of the images, the models just mix them together, and it don't know which one is which one. So it may not go to the right way to restore the image, but here that we through this way that we can the model can distinguish what is blood, what is low light, what is smoke, and then to restore them one by one better and better. Yeah, and this is the first part is around the image restoration, and the second part is like the interactive multimodal assistant. And in this task, it is something I have mentioned it before that we in surgical tasks we have a lot of different tasks, not only the action recognition, instrument grounding, and workflow recognition. We have so many tasks here, and we also have different data formats like the video, kinematics, and reports. So actually, we can unify not all tasks, like we can unify most of the tasks in text format. Like action recognition, it is actually a word of action. And instrument grounding, in grounding tasks, we need to output the bounding box, and the bounding box can actually be described by the text also. And also like the workflow recognition is also a word around workflow recognition. So we can unify all of these tasks into a simple vision language model. And the vision language model may not need to be a large language model, but a simple like encoder decoder kind of model can also do these tasks. And maybe let's see. So my first work here is around these tasks is to do the surgical visual question localized answering, and it is a multitask framework. And the first task we want to solve is the task-based question answering, and it is what I have said just now, that we want to unify all of these tasks into one single framework like this in the image in the right top here, and we can know what is the organ, what is the state, what is location, and what is operating, what is the action. And actually, in previous tasks, we need to use 4 different models to do this. But here, when we unify them together, we only need one model to do this kind of tasks. And also the previous VQA tasks, they just ignore the importance of targeted localization. So just imagine that this model is actually proposed for surgical education, but maybe the junior surgeons, they actually don't know which one is which instrument is which instrument. So they don't know the exact name. So if we can also output the localization, the bounding box of the target, it can better assist in the surgical education procedure. So here that also another straightforward thing is we just output a multitask framework, and besides the question answering, we give one more bounding box here, and to help by providing the where, what, and where, we help the junior surgeons and learners to better info why. And it is a very first work here in surgical, actually a VQA and grounding task. And also in following works, and I want to go deep into these works, and we want to just introduce more useful information here and to make it more practical. And in the left bottom one is we add the kinematics data into these tasks to make it better. This information into the model, it can better formulate the action, the workflow of the surgical instrument, so it can better understand the whole procedures. And also the right part is to do we want to try the robustness in the VQA task, that we have different kind of images. And what if I don't have a restoration? Can I just see through this robustness, see through this corruption and make a better robustness performance? And here that we just in the feature level, we add a visual perturbation here to and make a joint training of the clean visual embedding, a clean text embedding, and also a perturbated text embedding and a visual embedding. We make a mixed training here to make the model just learn from some perturbations here from the feature level, and then it can also can better distinguish in these corruption tasks. And also, so these works are mostly in 2023 or 2024, but now we have large language models, so we should think that how should we train another like multimodal large language model in the surgery tasks? And here we have the EndoChat, uh, and we all know that in ARM, the most important thing is we need to have a big data set. So without the data set, we can do nothing. But in certain tasks, actually, it's another problem in these tasks. Of course, we want to do an assistant. So an assistant is not like a very diverse area, and that we can answer everything of these thing or the input questions. We also want to regularize these ARM to a specific conversation types and also task types to cater the clinical need. So here we talk with surgeons and we ask them that what conversation type you want in this ARM and also what tasks you want in this ARM, and we can regularize this in our training data. So the ARM can actually learn from this training data to make it kindly formulate in these subtasks to give a better that output that surgeons may like. So here the surgeons they propose that we don't need a very diverse conversation with ARM. Maybe we only need these 5 categories here. So we have single phrase QA, we have detailed description, and we also have visual QA. And also the last two is region-based QA and grounding QA, and these two is about grounding tasks. So the fourth one is we have a question with grounding and answer is within this grounding, within this bounding box. And the last one is to answer a question with a grounding. So the surgeons they told us that they only want the model to be restricted into these kind of tasks, and when they want a single phrase answer, that's the model should not give a long description just like that. And also for region-based QA, that's the model should only discuss within this bounding box. And also for subtasks here, that's we set these kind of set for subtasks here. The most important one may be the auto instrument motion and motion direction, and also the object position here. So in the right part is how we collect this data, and here that the final part is obviously we use instruction training to make it a more diverse conversation types. But here that we first extract the key elements from the original images to just like a scene graph. And first we divide them into observations and operations. The observation is just like the instrument number, instrument category, and target issue. This is the basic information from the image we can directly extract from the original image. And for the second part is we need to get the scene graph connections between these every graph nodes. So this is the operations. This is a dynamic behavior understanding. Like we have the object position and instrument motion and also motion direction. So finally, we get this high-level semantic perception here. That it's just kind of a scene graph, and we have the interaction between the instrument and the organs, and also we have the location relationship between the instrument and the organs. So finally, this is just a demo of our conversation type here. And also we invite the expert surgeons to discuss that whether they are willing to use this model. But unluckily that there is still around 25% of the surgeons they think that it is they are not willing to use this model because of different problems. And this is also the future works that we need to do. But now I just put it here to show that we do have this evaluation, and still they have 75% of surgeons that agree to use us. And so I won't go very deep into the technical part, and maybe you can also search for this paper for the technical part of this work. And the data set is also open source, and if you want to play with it, you can just use it. Okay, and This is the 2D part, the 2D understanding part of the surgical scenes, and the third part is for the in vivo 3D perception part. And in 3D perceptions, and we know that in 3D perceptions that we have when we have the depth and estimation of the in vivo, we can know that what is the distance between the instrument tip and the organ. So we know that how long it will touch the organ, and we can give an prior warning or different info or any information the surgeons want of the 3D information here. So, but I want to divide the in vivo 3D perception tasks or the techniques into two parts. The first one is the visual odometry. Visual odometry is just like I would say it's more like a self-supervised depth and eagle motion estimation. It will estimate the depth maps by the depth and eagle motion. Um, it is. I will go through it deep. It is like a it is like a self-supervised framework, and it is actually supervised by the uh, uh let me sorry. It is actually supervised by the adjacent frames here, and when we have a depth map and we have the eagle motion, so we just wrap the uh, previous depth map into the next depth map by the eagle motion, and then it can have a supervision information to do this self-supervised task. So it is actually due by the it is actually due by the self-supervised system, and in this task we can actually use foundation models like the depth anything to give a prior here to make the to fine-tune the depth anything to get the downstream tasks performance. And another work, and I think most guys are familiar with the Gaussian splitting, and in vivo applications, it is like we can have the real-time rendering, and it is more lightweight, and we can generate a normal view, and it is so these two different techniques may have different user scenarios in vivo tasks. Like for the visual odometry, actually it can get better performance. So here, maybe it is more suitable for the geometry aware and also control-oriented tasks. So it can get better and more like the performance is better. But for Gaussian splitting, that maybe the performance will be not as good as the odometry part, but it can get better uh, photorealistic visualization, and it can use for some like augmented reality and also for view synthesis, and it can give a different view, a normal view for the surgeons to help them see better. And this is two basic technologies of the 3D task, and this is my understanding here. So in the first part, I will go through our work on the visual odometry, and I just briefly introduce the basic principle of these tasks. So the first work here is a MICCAI 2024 paper at NODAC. It's actually a dual stream framework. So I just mentioned it before. So here we have a dual stream. The first stream is a depth net. The depth net, it will get an depth output. And also another network is a pulse net, and it will give the eagle motion. And the eagle motion is actually uh, the the angle between the next frame and the current frame. So when you output two depth images here, and the eagle motion of these two depth images is actually not the same. So we need to use the estimate eagle motion to wrap the current frame into the next frame. So now they are in the same eagle motion. So then we can use these two images as a supervision information to get self-supervised supervision here. It is a basic idea, and also in the following two works here, and the first work is just like SLAM, we have VNS. VNS is like we have the vision input, and we also have vibration input. And here we by inject an IMU here, we can get an additional information with a vision block here to better understand the in vivo things with a new IMU to give it better performance. And in the right part is the most visual odometry works, they need the camera intrinsic parameter. So without this camera intrinsic parameter, that the model cannot predict very good performance. But here that we are thinking that whether we can remove the need for the camera intrinsic parameters. What if we just integrate the network together and now we have three outputs here. The output is by depth map, by the pose, and also the intrinsic information. And how to do this work is actually simple. So we just collected, we just first we fine tune from the foundation models, and we can also have a lot of endoscopic images with depth maps, and through this large scale pre-training and just through this fine tuning from basic foundation models, we can we found that through this pre-training, we can estimate the depth map without the intrinsic parameters through scaling law. So the idea is also simple. That's just scale up the data, and then we can eliminate the needs that trouble us for a long time. Okay. Uh, the following part is regarding the Gaussian splitting. So I say Gaussian splitting, the advantages for real-time reconstruction and also for novel view synthesis. So here is a the basic work here that this is Endo 40 Gaussian in 2024 MICCAI, and it's 3D scene reconstruction with 2D tour mask and depth prior. So here the input is the 2D tour mask, and also we use depth anything to give a depth prior here to reconstruct the map. And here the basic idea here is to see through the instruments. So we would like to see that what is under the surgical in the surgical instruments, but we only have a monocular view, so we want to synthetic the normal view here to see the whole view of the in vivo scene. And also following up works is to improve the method by varying different ways. And for the left part, it's we learn from the traditional SLAM works here that we will have the tracking and mapping here. Here we also estimate the camera trajectory here. So via the camera trajectory here and via our 3D Gaussian, and we can combine these reconstructed surgical scenes and the estimated camera trajectory here to make it just like SLAM. We can not only synthesis novel view, and we can also construct the whole surgical scenes, and like we can reconstruct the whole stomach through the endoscopic image. And in the right part, it's combined with previous low-level tasks here, and we want to reconstruct and rendering under complex illumination condition. And also, how we do this is also similar, that we extract the low light or the overexposed information as in prior, and we extract it by model, and then we inject this prior into the MRP to initialize the point cloud. Okay, we just go through the next work. The next work is also last year's MICCAI Young Scientist Award, and this work is also application driven. That we are thinking that previous in MICCAI 2024, we have a lot of Gaussian splitting work in endoscopic scenes, and we also have a lot of works in 2D semantic segmentation in endoscopic scenes. But what if we can combine them together? So 2D endoscopics, they don't have novel views, but we still need two model to combine them together, and we need to like remapping the 2D into 3D, but we cannot get a real-time rendering and segmentation together. So here that is the work what we want to do. That what if I only give one text input, and we can get the 3D rendering and also the 3D segmentation of the target by the vision language query. So here the basic idea is to use SAM first to extract the semantic embedding here. So we can see here, actually SAM is used here to on the original 2D images to get the basic semantic understanding of the whole image, and we can get the semantic segmentation here. And then we in the last parts here, we match the vision language query with semantic understanding here to match them together. So now we can, through the last part here, we can know what text is corresponding to which part of the image. So this is a basic idea of that. And the final performance is like this. And when we input a single word or a single name of the instrument, and we can render in the 3D and also get the 3D segmentation of the results. Okay, and that is what we do in the 3D part. And in the last part is what we do in generative AI here. So as I say that most of my work is actually within the maybe computer vision or the perception tasks, but in this work, we would like to see that what generative AI can do in the true actuation tasks and also to simulate the future surgical procedures. And then hopefully that we can make it a world model and it can in the loop to do the work, and we can see vision interaction will predict the next actuation in the procedure, and also video generation can predict what will be the next progress, and it can be a warning or prediction information to feedback to the VRA, and then it can know that what will happen in the future, and then it will be in the loop VRA and video generation. So here that then I will divide this work into two parts. The first part is for vision language action, and another part is for video generation. For vision language action, and actually, I would say it is not a very the model is not very important, or the ARM and the training procedure is not very important in this work set. What you need to do is to collect good data to train this theory. So the idea is like we have an instruction here for tracking, and in vivo tasks like we have an endoscope into your body, and we want it to track the polyp or the abnormal region by itself. So our instruction is like you are an action director, and the target is a polyp, and you need to track this target by yourself, and you need to output the next step with the motion and also the bounding box. So you need to do the detection first, and then you need to output the motion that what you need to do in this tracking procedure. So the input is language instruction and the current step motion, and the output is object bounding box and the next step motion. And then it will be an in the loop training here, and then every time it will output the next step and out next step, like just like this. So we have two work here. The first work is in flexible endoscope, and another is in capsule endoscope. So I would say the training procedure is very similar, or the very simple as the normal in the general scenarios of the VRA training. And the first part we have SFT, and another part we have reinforcement fine tuning. And in the reinforcement fine tuning, our reward is first the IOU reward. Of course, we need to do detection. So IOU is our reward. And also another reward is a format reward. We want the output into the good format of the IOU, and also the angle. The angle is the motor angle that the actuator. And the last part is for the MA reward. The MA reward is actually the motor angle, and we have two degree of freedom here, and it will output the angle of the motor, and we will calculate a difference between the ground truth to train the model. So the whole procedure is actually I would say the only thing we do is to decompose the tracking procedure into first bounding box prediction, and then we output the motor angle here. This is only design here, but other part is all the same with previous reinforcement fine tuning tasks here. So however, we construct this system in the left that we have this motor and also a flexible endoscope, and we collect the data also in the simulation in a fine tune. First, we collect data in the simulation, in computer simulation, so I just guess the system. It should be a very popular system, sorry. And then we collect the data in the fine tune, and then the last part we collect the data in like a pig stomach. This kind of this to construct the whole procedure from computer simulation to the fine tune simulation, and then to the ex vivo tasks, and then Now we are trying to see that whether we can do true in vivo in live pigs, but now we are doing some trials here. So this is steps we are doing in vision language action. Another part is, I would say, the surgical video prediction. So just now I say that if you can have if you know the next step of the surgery, so can we actually predict the future surgical videos? So I can give if we given a first frame and also we give some action information, and then can we generate the future 3 to 5 seconds based on the given information? So we can actually know what the surgical process will go to, and we can know that whether it will make some dangerous or we can get some warning to the surgeons, and then they can know that, oh, this is right, so we can keep going on, or this is not right, that we should be careful. So in this work, for now, this work is not an in-the-loop work with the VRA1, and we hope to do so, but in this work we didn't do that. So this work is actually by the given information is also the first frame, and another given information is by the arrow. The arrow includes the direction and the magnitude of the instrument or the organ. So here we invite the surgeons to annotate the error here that given the previous image and given the previous frames, several frames, and what they think that these instrument and the tissues should going on. So they annotate such kind of the arrows, and then we extend these arrows into an optic flow field to serve as a guiding information, just like this in this part. And we can get optic flows, and these optical flows will be the guided information for us to fine-tune the stable video diffusion model. So here we can see the performance. Just like this, we hope to predict the next 3 to 5 seconds based on the arrows drawn by the surgeon. So why we like this setup, we use arrows to do arrows to do these things, because we try different kind of ways, like we try text supervised generation, or we try just unconditional supervision. But in unconditional supervision, that it's not useful. So it cannot help us to predict the next progress. So it's in this setup that it is not useful in our setup. And for the text, it's for text to video generation, and I think it's a lot of people would do such kind of works. But we found that if you do text to video generation, your text must be very, very careful and very, very detailed. In other way, that if your text is just one sentence or two sentences, maybe that it will cause overfitting. Of course, uh, there is a lot of different surgical actions can corresponding to a single sentence to describe this video clip. So if you only input a single sentence of the video clips, that it will generate these different kind of surgical videos, but all meaning a same surgical procedure, or meaning a same caption. So in this way, that it may lead to overfitting, and it will not be very controllable. So for text to videos generation, that we are thinking to get better and detailed annotation here to do that. But for this work, that we are thinking a more straightforward way, that we just give an arrow of the image and it can get a video generation better. And this is a basic idea here. So I just go through the next steps because it's similar with actuation and simulation. So what if that we have a surgical foundation model, and maybe you guys have seen this work from NVIDIA, the surgical world model work, and they just talk about real data and synthetic data. But here that I think every single part here, from real data, synthetic data, and joint training, they can be in the loop help. They can be in the loop system, that every part can help another part by somehow. So like the real data, it is the basic data for generation of the synthetic data, and also that we have a surgical foundation model, and we use the real data of the downstream task data to generate the generation model, and then it can generate synthetic data. And the synthetic data can go back to do the progress prediction and warning to the real operation. And for the VRA parts that we have the synthetic data and the real data, we join the training and we get a VRA policy. So uh, a big problem of surgical VRA is that we don't have enough data, and every single task we need to collect our own data set. But here that we can have like generation way to generate the synthetic data and the synthetic kinematics, and we have real data and real kinematics, and then we can combine them together to join training. And through this large scale training, we can get a, a suitable and a trustworthy VRA policy to apply on the real surgical robot to see it can actuate better in the system. Okay. But for now that I haven't do this work, maybe somebody here will do, and maybe somebody in the world will do this. And I think that it's accessible. It's accessible, and maybe let's see that's how we can do in the automated surgery, how we can advance the process of the surgical robots. And also thank for all of my supervisors, advisors, collaborators, and also clinical partners. And also, I would say sorry for again, of course, these slides that I just finished the slides the first time. So this is also the first time I talk about these slides. So maybe sometimes I will not be very fluent about that. So sorry for that. And thank you everybody here to listen to my talk, and I'm happy to accommodate any questions. Thank you.
No, thank you so much. This was a really great talk. I think, I didn't realize that it was your first time talking about these slides. So I think you did a very good job explaining everything. Um, yeah, I guess we can just dive right into questions if anybody has any. We'll do public Q&A, but also if somebody doesn't want their question included in the final video that's uploaded to YouTube, we'll have a private component too. Anyone who wants to open it up? If not,
Um,
yeah.
hey, thanks for the presentation. This was fantastic. I'm wondering if you've thought about the sample efficiency of imitation learning versus learning and transferring from simulation, and if you have any thoughts as to what is going to be the better approach in the short to medium term.
I would say maybe you have seen the work from Johns Hopkins. They do also from the Chinese University of Hong Kong that they already do like this kind of imitation learning that's in simulation parts, and where we can do this, we can formulate the surgical procedure in the simulation very simple, and then we can do imitation learning from the simulation. And for current works, I think that they can now do like 10 or 20 seconds of automation procedure. And it is definitely a very doable way to like move on from the uh, imitation. I would say imitation learning is definitely a doable way here from simulation to real data. Of course, like we have tried joint training, but joint training is actually it still has domain gap. Like we put the synthetic data and or we put the simulation data and the real data together, and this data, the the target is different, like the polyp is different, and also the instrument is not very similar. So they will have a domain gap, and the improvement of the performance is actually not very, uh, not as much as our we expect. But for imitation learning, I would say like you just need to imitate the procedure of the surgical instrument, and then that I would say it is easy way for the model to learn from that, I would say. So, but it is my own opinion, so I'm not sure that whether you also think about that or whether other guys agree with that.
Oh, thank you. That's very helpful. Thank you.
Yeah, thank you.
I have a question. So I work on neural rendering, I guess more for colonoscopy, and I'm curious how you're thinking about kind of the future of where that's headed, whether it's like a piece of this, I guess you talked about next steps in the last slide, of just these world models, or if it's something that's more for like training like new generations of physicians, or something else. I guess, yeah. How are you thinking about like Gaussian splatting? If it's just like a piece of the puzzle, or it's its own thing?
Uh, 'Cause I'm currently actually trying to do some work to combine the Gaussian subletting with 3D video generation. Of course, I keep saying that we need to have the 3D perception in vivo. So if we don't have the 3D perception, maybe we will ignore a lot of important information, like the distance kind of things. So uh, but just like when we do 2D image, how do you say that? So let's think by two ways. The first way is now we do 2D video generation. And for 2D video generation, that obviously we need to get the physics information. So here that I would say maybe we guys are trying to like use depth estimation or also Gaussian subletting to here to uh, get some physics information, and for 3D rendering here to help the model to better understand the 3D perception here to get a better, a more realistic 2D video generation. This is the first one. And the second one, and I'm thinking that for generation, for video generation, can we just directly generate the 3D videos instead of like we generate 2D images or 2D videos, and then we still need to extract the 3D information from these 2D from the 2D images or videos. Of course, like if we can have the ground truth 3D, not only ground truth, maybe the rendered 3D objects, like now SAM 3D can do this. So we can have the target that the instrument is actually extract here, and we have the 3D objects of the instrument, and like we can just generate the next 3 or 5 minutes of 3 or 5 seconds of how this 3D target is moving, and in this system. So this may be more helpful that the surgeons they can see that wow, we have the 3D video that's how the tissues and the instruments are moving, so we can better know that whatever going on. But for 2Ds, and they cannot see the future very clearly. But for 3D generation, they can see it very clearly. So I'm thinking, but I'm not doing this work. Maybe you guys will do that. I don't know.
Yeah, yeah, no, it's something that I'm thinking about too. So I guess in your mind, you're seeing him kind of as a like almost like a physical grounding mechanism for video generation, or for creating something that's well, physically meaningful or grounded in physical reality. Is that what you're saying?
Uh,
For the,
Kind of like that.
gout?
Yeah,
Yeah, okay.
yeah.
Makes sense. Um, nice. Does anyone else have any questions? I have some more as well. Okay, I can just keep going. Um, so at the start, you were talking about image reconstruction. I guess related to maybe my previous question as well. How are you maybe thinking about integrating kind of all of these different papers and these different approaches into something, more unified? Is it kind of all feeding into that last slide that you showed, where you just um, have, you know, something that's trained like fully on synthetic data, incorporating kind of everything, or like this training between
Yeah,
synthetic,
yeah, yeah.
real. Yeah.
Yeah, I got your point. That actually I'm still missing one slide here. So in before this slide, and I should have a slide, but I didn't have time to make it. So let's go into this one, this slide, this page. Uh, So here we can see actually it can formulate a system like here first we do the restoration. So the first problem is to do the restoration, that to solve these corrupted images, and this is the very first problem. Like it's in the very left part that we need to do this first, and then the section 2 and the section 3 should actually be a parallel, that we jointly we do the multimodal understanding. It can interact with the surgeons and give the surgeon or the model a guidance from the vision language model. And also that we should also give the model the 3D perception and give the surgeon or the model that they can do the two perception together. One is vision energy perception and another is 3D perception. And then we can give them these understandings together to formulate their basic understanding of the theoretical things. And then in the final part is that we have this understanding. We already restore the images and we also have these understandings, and based on all of this information, now I can do the actuation right now. And then after the actuation, then we can use the video generation to do the word model, to do the in-the-loop training of the VRA and the video generation. And this is my hope, but so it I don't know when I can finish all of this.
Fair enough. Yeah, no, that's very cool. Thank you.
Thank you for inviting, and hope you guys enjoy the talk and have a nice day. Yeah.
All right. Thank you so much. Bye-bye.
Thank you.